Scores, key, posted. Exam 3. I decided to value each question at 13 a pop. I usually raise the point value per Q as the term proceeds. If for no other reason but to provide a little bit more reward for those of you who are good enough to stick with this gathering. We proceed. Chapter 21. Talking now about applied thermodynamics, practical thermodynamics. For example, how do we use thermodynamic data, like we see in Table 1 at the end of Chapter 20, to support our ability to analyze a system from a thermodynamic standpoint. With that, we looked at this system. Calcium carbonate decomposing into calcium oxide and CO2. We recognized that with the data that comes from Table 1, delta S0 for this reaction is favorable, as you would well expect, which we discussed last time. But delta H0 is much larger than T delta S0, and delta H0 is endo. It's again this process. Upshot, under standard state conditions, this process is not spontaneous whatsoever. The equilibrium constant is partial pressure of CO2. If we need units to apply to the calculated K value, because again, when you calculate a K value from thermodynamic data, you get a unitless quantity, given that by definition K values are unitless. But from a practical standpoint, oftentimes we need to attach units to K, like this case. So, when with the thermodynamic data, in conjunction with this relationship, I think last time I might have wrote RTLNK. If I wrote that, that's not right. Because the 2.3 multiplier converts natural logs to logs base 10. I much more often use logs base 10 because of all the pH arithmetic we do. So, after getting delta G0 for this reaction, we calculate K, there's the K value. Then we ask the question, what's the significance of this K value? To get at the significance of this K value, we imagine a sample of calcium carbonate at 25 degrees centigrade. External pressure of 1 atmosphere. In a 10.0 liter volume sealed flask containing calcium carbonate and an atmosphere of air which we have taken steps to make free of any CO2 molecules. Under these conditions, will the CaCO3 decompose? Answer is yes, until a partial pressure of CO2 of 2.3 times 10 to minus 23 atmospheres is attained. How much CO2 is this? Well, we'll treat CO2 as a gas whose behavior is describable by PV equals nRT. A fair statement because CO2 is not a polar molecule, nor does it have a particularly substantial formula mass, so London attractions will not be extreme. And we find that in the 10 liter volume, with CO2 at this partial pressure and this temperature, that's 9.4 times 10 to minus 24 moles. That's an awfully tiny number. So we ask the question, if we were able to observe the inside of this flask, its contents, and had super magnifying power glasses, so we could see CO2 molecules, how many would we see? Well, we take moles and multiply it by Avogadro's number, which counts up molecules per mole. In this case, molecules of CO2. And if in this case you pay attention to significant figures, you'll get 5.7 molecules. But we know there is no such a thing as 0.7 of a molecule. Just like there's no such a thing as 1/3 of a chair. I can take a chair apart, but after I take it apart, I got junk. I don't have a chair anymore. So I'll round this to the nearest whole number, since molecules are integral units, and get 6 molecules. Count them up. 1, 2, 3, 4, 5, 6. So now we know for sure that in the air atmosphere of our classroom, there will be 0 decomposition of any sample of calcium carbonate. Absolutely none. Why is that true? Do you think per every 10.0 liter volume of this air in here, we've got more than 6 CO2 molecules? There's a hell of a lot more. Because CO2 is a product of human respiration. We inhale the oxygen, and much of the oxygen we inhale is converted to CO2. Much of which is expelled when we breathe out. So I breathed out and put a hell of a lot more CO2 molecules in here than 6 per each 10 liter volume. Next question. The next question is aimed at the fact that calcium oxide, a product of this reaction, is a very important commercial, industrial, chemical material. The last I checked, in terms of tons produced per year, calcium oxide was in the top 10. I don't know if it still is, but I know it's still a material which is produced in great quantity. How do you think calcium oxide is commonly produced? Do you think calcium oxide might be produced in the state of Florida? Are any of you Floridians? Are any of you Floridians, for example, from the Tampa, St. Pete area? Now, I don't know if this company is still there, but a while back I researched this somewhat and found a company called Loncala Phosphate. Loncala Phosphate did, and if they're still there, I imagine still do, dig into Earth's crust, where calcium carbonate and calcium phosphate and calcium sulfate deposits are rich. Now, Loncala Phosphate in the main is interested in phosphate, calcium phosphate. But if I want to make calcium oxide, I can make it from any of these 3 materials. How do you think, if my steam shovel goes down into Mother Earth in the Tampa area and takes a big bite of this calcium salt deposit, calcium phosphate, calcium carbonate, calcium sulfate, what do you think I'd do to these materials to get calcium oxide? Do you think in doing this I might find any calcium oxide by itself? Think I might find some calcium oxide existing in this sample of Earth's crust? Think so? Calcium oxide's too damn reactive. Put it in contact with water, converts to calcium hydroxide. Put in contact with CO2, converts readily to calcium carbonate. Hey, you realize that 25 centigrade, that K for the conversion of K for the conversion of calcium oxide in the presence of CO2 is 1 over that K value. That's one hell of a big number. Not going to find any calcium oxide. Now, there are some oxides which you can find existing naturally, because the oxide ion component in these materials is not reactive at all. You know any oxide materials which are found in nature that are quite stable? Silver oxide? Nope. Iron oxide, you can find iron oxides. What else?
Copper oxide?
I don't think you'll find any copper oxide. You ever been to the beach? What are you standing on? What the hell is sand? Mainly. Silicon dioxide. How about that? How about CO2? Carbon dioxide. We got any of that around? Sure. But these molecular oxides do not behave like metallic oxides at all, because the molecular oxides are not ionic. Nevertheless, they are known as oxides. All right? After having mined calcium carbonate, what do I do to turn it into calcium oxide? Same treatment would convert calcium phosphate ultimately to calcium oxide, as well as calcium sulfate, gypsum. Heat it. Remember that delta S0 is for this transformation? And how do we magnify the impact of delta S0 for a reaction? Up to temperature. So the question then is, what temperature do we have to achieve in order to get calcium carbonate to decompose spontaneously under standard state conditions? Now, do you understand the question? We want calcium carbonate to be able to decompose spontaneously under standard state conditions. What temperature must be achieved to do this? What temperature must be established to achieve this, I should better say? Calcium carbonate is decomposing under standard state conditions. What does that mean? That means that reaction is going, okay, and the equilibrium constant for that reaction tells us the only term we have to consider for this reaction regarding the question I just asked is which term? What's in the equilibrium constant? Carbon dioxide. So we need a temperature condition for which calcium carbonate will continue to decompose in an atmosphere of CO2, which is at what partial pressure? 1 what? 18. Yes. So let's take a look at the equilibrium temperature, because that we can get from this. Do you realize when this condition exists, the value for delta G0 is how much? 0. Look at this. Because if calcium carbonate, if the equilibrium constant for this reaction has a value of 1, with the unit being atmosphere, if the equilibrium constant for this reaction has a value of 1, Because we know the equilibrium constant for this reaction is going to get bigger and bigger and bigger as we heat the system. Because T del S is getting bigger and bigger. And that favors this reaction. So now the equilibrium constant has a value of 1 atmosphere. What's a log of 1? 0. How about that? Delta G0 is now 0. Okay? And when the delta G0 is 0, for this reaction, because the partial pressure of CO2 is now 1 atmosphere, then delta H0 equals T del S0. So can I calculate the temperature? Because I have the delta H0 value and I have the delta S0 value. Now, this temperature will not, the temperature we calculate will not be exactly on the money. And if you do some higher level chemistry studies, like in PChem class, you'll learn that delta S0 and delta H0 are not entirely isothermal. What's that mean?
Same for all temperatures.
Isothermal means independent of temperature. Those values for delta S0, delta H0 for reaction do change slightly as I change temperature. And we're going to change temperature considerably. So the values we're going to use for delta S0 and delta H0 are the values we had for 25 degrees centigrade. They changed somewhat, but not very much. We'll not worry about that refined detail of this consideration at this stage of the game. We'll use the values we had, and in using the values we had, you can put in the numbers. You've got the numbers. I think you get a temperature around 1100 centigrade. Let me see where I have it here. Someplace in my scribbly notes. 1091 K. So, if you add 273 to this, you'll know the temperature in centigrade. We don't care about that. Which means, if I want this decomposition to proceed spontaneously at standard state conditions, what temperature do I have to achieve relative to this temperature? A greater temperature, that's right. So, heat above 1091 K. Now, if you do this decomposition in a closed vessel, it won't proceed very far because shortly the system will come to equilibrium. Because the partial pressure of CO2 will now raise to a value that's above 1 atmosphere. But if you do this composition in the open atmosphere, it keeps on going. Because the external pressure exerted by the open atmosphere on this system is 1 atmosphere. So when the partial pressure of CO2 builds up such that it's somewhat greater than 1 atmosphere and the system is not closed, the CO2 produced by this reaction keeps shoving away the atmosphere. Pushes the oxygen molecules and the nitrogen molecules away as CO2 comes into the atmosphere from this reaction. And that's the way they do it. You want to produce calcium oxide industrially? Get a whole bunch of calcium carbonate and heat the hell out of it. The temperature above that. And you got it. Now, after you do this, you better keep the calcium oxide you make away from any CO2 containing atmosphere. Because this reaction also tells you, if you have a closed atmosphere, you want to do some chemistry in this closed atmosphere, and this closed atmosphere in which you wish to do the chemistry must not have any CO2 molecules in there, because the CO2 molecules will adversely affect the chemistry you wish to study. What can you do to purge an atmosphere of CO2? Closed atmosphere. Yeah, as you walk around chemistry, you'll see in laboratories these things they call dry boxes or glove boxes. It's a big chamber. The front of the chamber is usually made out of plexiglass. It's mounted in a metallic cabinet. It's got a sealed door on the end, so you can open up the door, go in there, and you can pump out the atmosphere with vacuum pumps and things like that if you want to do that. Or in this case, you can go inside this sealed chamber and then pump out the atmosphere and admit a cylinder full of nitrogen. Admit nitrogen from a cylinder of nitrogen, so the only atmosphere you got in there is nitrogen. Or whatever you want. Argon, whatever you want. Nitrogen, argon are pretty inert atmospheres. Nitrogen molecules, not very reactive molecules. That triple bond in the N2 molecule keeps those things damn stable. Okay? But another way by which you could free this atmosphere of CO2 molecules is to open up the door and put in there a big tray of calcium oxide. Close the door. Because that calcium oxide is going to pull the CO2 molecules out of there pretty daggone fast. Particularly if you have a fan in there to keep the atmosphere flowing over the calcium oxide. Then through these big rubber gloves, which you also see on the front of this box, you stick your arms in there and you now have your hands inside, but insulated from the contents of this sealed atmosphere. And you do your chemistry in there. Neat. It's interesting. You got any question? Now then, there are some additional questions attached to this transformation, which I will have the discussion folks deal with for your benefit tomorrow in discussion class. I will jump to question 39 because I want to do some more. Let me get our sample out here again. I want to do some more analysis on this system. Remember this? We recognized from what we talked about previously regarding this system, where the observable stuff, the brown gases, are NO2 molecules. That in this, not only do we have colorless N2O4 molecules, most of the molecules in here are N2O4 molecules. Because the analysis we made on this system previously told us that 1 mole of N2O4 at 25 centigrade 1 atmosphere is thermodynamically more stable than 2 moles of NO2 gas. But regardless of which pure component you might choose to start with, if you were able to do this experiment, you would not get complete conversion of one of the molecules to the other. You would not get complete conversion of all the NO2 molecules to the N2O4 molecules, given that we recognize that the N2O4 molecules are thermodynamically more stable at 25 centigrade 1 atmosphere total pressure than 2 moles of NO2 molecules. What would you get? You'd get the equilibrium system. So in here, beside the brown NO2 molecules, we have mainly colorless N2O4 molecules. I want you to take a look at the G-state graph, which we discussed previously for this system. I believe it's on page 8 in chapter 21. But don't quote me on the page number, but I think it's page 8. That's it, page 8. The G-state graph shows us that if I were able to do the experiment which we discussed previously on starting with 1 mole of N2O4 in a piston cylinder apparatus at an external pressure of 1 atmosphere and temperature of 25 degrees centigrade, about 20% of these molecules, of the N2O4 molecules, would decompose and become these colored molecules, NO2. Remember that? Let's see if we can prove that. We'll prove that by analyzing this composition of this system at equilibrium at these conditions. Now this follows question 2139 in the notes. The way question 2139 is written in the notes, we have this same equilibrium reaction but in the opposite direction. So I'm going to do the analysis for the reaction written in this direction, and then if you need additional practice, you can do the analysis on question 39. Same system, except that the directionality of the reaction is reversed. Okay? Start with K. First, let's write K chemically. What is the equilibrium constant for this reaction? I trust you all know this because I asked you about this on exam 2. Do you remember that? How about that? Dirty rat Horvath strikes again. Hell, you knew how to do this from chapter 17, which is what we started with. Got this? All right. Now we're going to get the data from Table 1, end of chapter 20. You get the data. I'm not going to write it on the board. Calculate delta G0 for this reaction at 298 K, 25 centigrade, so that we can get K. The number we get is 6.69. Let me check. Yeah. What are the units on this number?
Atmosphere to negative first.
Mm-hmm. 1 over atmospheres. That's the units, right? Because this is atmospheres and this is atmosphere squared. Hey, you got to let the system talk to you. What do we do now?
Dr. Horvath, how did you get that value from delta G?
From delta G0. I'm in the thermodynamic properties data table. Okay? In the thermodynamic properties data table, I can do one of two things. I can look up delta H sub F super 0 for this, delta H sub F super 0 for this, S0 for this, S0 for this. I apply Hess's law to each, put them together in accord with delta G0 equals delta H0 minus T delta S0 and get delta G0. Or I can take the delta G sub F super 0 value straight away. They're in that table. Okay? Apply Hess's law to that, get delta G0 for the reaction.
Don't you take just the straight delta G of N2O4 minus the delta G of...
Delta G0.
Yes, sir.
Go ahead.
Minus the delta G0 of NO2 minus...
You get... If you want to get delta G0 straight away for this reaction, you will get delta G sub F super 0 for this, less twice, see this? Less twice delta G sub F super 0 for this. And that'll give you delta G0 for the reaction. Then you put delta G0 for the reaction in there and calculate K. You know T, that's 298K. You do the arithmetic. You need to practice. If you have difficulty with the arithmetic, you can always ask us. But bear in mind, this is an arithmetic question, not a chemistry question anymore. All right? Here's our K value. What do we do now to pursue the issue of calculating the composition of the system at equilibrium? We want to see if we can verify this 20% decomposition value, which you see given in our G-state graph, which we've already looked at for this very same system at the same temperature and pressure condition.
partial pressures of both gases respectively?
That's right, Dalton. Let's get at it, Dalton. You learned about Dalton in 2045. Let's put Dalton to use. What does Dalton tell us regarding partial pressures of gases? Or put another way, what are the two aspects of Dalton's law of partial pressures? Tell me. You learned this? I want to now know what it is, because you learned it. Go ahead.
We know that the sum of the partial pressures is equal to the total pressure.
Bingo. In any gas system, Dalton's law tells us that total pressure on the system, we'll write that down, P total. What's P total for this system? 1 atmosphere. I'll write it to 2 sig figs. Equals P NO2 gas plus P N2O4 gas. There's only 2 gases in this system. So how do I write the partial pressure of either gas in terms of the partial pressure of the other gas?
1 minus.
No big deal. I can write, let's see what I did. I wrote PN2O4 gas equals 1.0 atmospheres minus PNO2 gas. There's application of Dalton's law, step 1. So now we have a way to calculate the partial pressures. How do we proceed? How do we now calculate the partial pressures? Put them in this, right? I'll rewrite this as PN2O4 gas up top, 1.0 minus PN2O4 gas quantity squared down below, equal to that. I got one equation, one unknown. The unknown is PN2O4 gas. Now how am I going to solve this puzzle? Am I going to expand it and turn it into a quadratic equation? Like hell, never. It's a waste of time. These stupid damn textbooks which teach you to do it that way are stupid. Because they stand in the way of your understanding of chemistry. I agree that sometimes using the quadratic recipe is utilitarian. But most of the time, it should not be used because it drives students in chemistry class, particularly first-year chemistry class, to look for a recipe in which to shove data and push buttons on the calculator rather than think, and I won't stand for that. All right, we know how to do the calculation. I'll write the results. PN2O4 calculates to be 0.68 atmospheres. Then PNO2 gas must be 0.32 atmospheres. Because I just take 1.0 atmospheres total pressure, subtract this from 1.0 atmospheres, and that's it. All right? We now got the partial pressures, but I want composition. Composition means at equilibrium. What will be the mole ratio of these gases to each other?
Isn't it the same as the ratio of the partial pressure?
Oh, no, it isn't. Use PV equals nRT. Now, if we try PV equals nRT, Remember, what we want to get is this, okay? We don't know moles. We know this. Do you know this? Forget PV equals nRT, because that's a recipe with two unknowns. You can't solve it. Keep in mind, if I imagine to do this experiment as we have previously discussed, one mole N2O4 gas. Is this going to sit there? No. This is going to decompose. About 20% thereof, 20 mole percent, if you believe our G-state graph, and that's what we're trying to verify, into NO2 gas, which means as this thing reacts to get to equilibrium, the volume is getting bigger and bigger and bigger inside. But what is the internal volume achieved? It can't be an internal volume which is equal to twice this quantity, because it doesn't go to 2 moles NO2. In fact, it only goes about 20% if the G-state graph is correct. But we don't know just where yet, because we don't know moles, do we? So we don't know volume. So forget PV equals nRT. Can't do it that way. How can we do it, Professor Dalton? Because Dalton's law of partial pressures has two aspects. We've talked about one aspect, we applied it. Total pressure gas system is equal to sum of the partial pressures for the component gases, and this is a two-component gas system. What else does Dalton's law tell us? What does Dalton's law tell us about moles of a gas relative to partial pressure for that gas? Come on, you did this. Let's put it to use. Are we not remembering this? Well, for $25, I will tell you. $50. $100. I'm going to write a symbol on the board. You seen this before? Capital version Greek letter chi. What does that mean, Dalton? I heard it. Mole fraction! Ha ha! Because the other part of Dalton's law is that. The partial pressure of a gas in a gas system, NO2 or N2O4 for our system, is directly proportional to its mole fraction. And that's what we need. All right. Well, let's see. This time I'll monkey around with NO2. I'll stick with N2O4. PN2O4 is 0.68 atmospheres. So we'll write this again. This is Dalton's law, second application. There's the total pressure application. Two other small erasers up here last time. There must be an eraser rat around here someplace. Ate the erasers. I hope the damn thing dies on the chalk dust it is ingested. Teach it to eat my erasers. What do I write up here?
The moles of NO2.
Nope. This is partial pressure of N2O4. What do I write down here? What do I take this mole fraction expression, that's what we just wrote, what do I multiply the mole fraction expression by to make this an equality?
Total pressure?
Yes! Well, as written, I have two unknowns, don't I? All right, so let's try this approach. Oh, I erased my piston cylinder, damn it. Let's go back and revisit the piston cylinder, which we imagined to contain initially 1.0 moles of N2O4 gas pure. As time passes, we know this N2O4 gas is going to fall apart to some extent and become NO2 molecules. Okay? But I'm going to start with 1.0 moles of N2O4 gas. All right? Starting with, so this is initial quantity. At EQ, we'll have 1.0 moles N2O4. Well, let's just write 1.0 moles. Minus how much? How do you wish to represent the amount of N2O4, pardon me, amount of N2O4 which fell apart and became NO2?
Minus the number of moles of NO2 divided by 2.
Why do you want to divide by 2?
Because for every mole of N2O4 you lose, you get 2 moles of NO2.
I agree with that. So what do I want to subtract from 1.0 moles of N2O4? Well, let's write it this way. Let X equals moles NO2 produced. Is that all right? All right. Or if you prefer, I can let 2x equals moles NO2 produced. Whatever you want. Because, you see what this fraction tells me? As you just stated, as a mole of, as 2 moles of this disappear, I get a mole of this. As 1 mole of this falls apart, I get 2 moles of this. I'm just letting this thing talk to us. So if X is moles of NO2 produced, how much N2O4 fell apart? X over 2. I don't like X over 2. So I'm going to say let 2X equals moles NO2 produced. Then, there's nothing wrong with what you said. .0 moles minus X is moles of NO2 I got at equilibrium. And 2X equals moles NO2 at EQ. And these are the mole quantities I want, because I want to get the composition of the system at equilibrium. Well, now I got what I need. So I'll rewrite this as 0.68, because now I can take away atmospheres from each side of this equation we wrote based on Dalton's law of partial pressures. 0.68 equals X over 1.0 minus X plus 2X. Think you can solve this? One equation, one unknown?
Why isn't the top 1.0 minus X?
What is what?
Why is the numerator 1.0 minus X?
It is. Oh! Pardon me. Yes. Pardon me. Good. Otherwise I had this all fouled up. Okay? Can I solve this? Of course. Solve. Get. What do I get? Write it down here. 0.81 moles N2O4 at EQ and 0.38 moles NO2 at EQ. Now keep in mind, our G-state graph indicates, if the G-state graph is drawn in accord with data, that about 20 mole percent of N2O4 comes apart to get us to equilibrium, right? Is that what the G-state graph says? So I imagine to do this experiment starting with 1.0 moles of N2O4, and I wind up with an equilibrium quantity of 0.81 moles. Is that about 20% of it went away? That's it. So what we now know is that for the NO2, N2O4 system to be at equilibrium at these conditions, okay, we must have a mole ratio of NO2 to N2O4, which is about 0.38 divided by 0.81. Or if you want to turn it around, a mole ratio of N2O4 to NO2 of 0.81 to 0.38. The ratio is about 2 point something or other. Didn't write it down. Oh, here it is. About 2.1 to 1. That's 0.81 divided by 0.38. All right? So now I know. I don't care what mix I start with of NO2 and N2O4. I don't care what the mole ratio is, what I start with. If I'm at these conditions, that NO2, N2O4 system will react until I get a mole ratio of N2O4 to NO2. That's about 2.1 to 1, because now I'm at equilibrium. And that's it. We'll ask one or two more questions on this next time, and then we will be in chapter 22 on electrochemistry. Get at reading and studying such.